Module 20 Comparing Proportions, Section 2, Risk, NNT, Odds Ratio, Fisher's exact test and binomial test. Case control usually express that in 2x2 contingency table that we have already seen that in data summarization module. So it's also known as two-way table. So in this kind of table there is only two columns and two rows. So the columns are usually outcomes while the rows are usually treatments or the groups. One example is lung cancer. The case and control are the outcomes, that is in lung cancer group as well as a healthy group. Control group which there is no lung cancer, they are arranged in the columns, while in the rows they are basically smoker and non-smoker. So it's an example of a contingency table. So these kind of tables that we use often for categorical data. So one example for a prospective study is that a randomized double-blind prospective study. So all these terms I have already explained to you when we discussed about different types of studies in module number 2. So this is randomized and it's double blind, and prospective means going ahead in time, So to find the effects of apixaban, that is an anticoagulant, on the recurrent thromboembolism. The thromboembolism means the blood getting clotted somewhere, especially in the leg, and if it's actually getting loose, it can go to the lung and cause serious problems, even death. So what is the effect of this blood thinning coagulant apixaban on those people with thromboembolism, the recurrency rate? To know that, this is a summary of that table, summary of that prospective study. So here you see the columns are basically recurrent thromboembolism or no recurrence among the people that they did this epidemiological study performed, and rows are nothing but placebo. Instead of giving the no medicine, they are giving something in a pretext that it is basically a drug to control the psychological effect or bias called placebo effect I have explained to you in the first module. So, and the first row is placebo, while the second row is apixaban, that is 2.5 mg twice day. That is by Agnelli et al. In 2012 is the paper. You can have a look at that paper as well. So this is the original data from that paper. So this you can see that these numbers are basically the observed frequencies, empirical frequencies. Let us also put the total there, and we can also express that in proportions as well. Now let us calculate the incidence rate. So incidence rate is nothing but number of cases by the total number of persons. So we can do that, number of cases by the total number of persons. So number of people having recurrent thromboembolism divided by the total number of persons is the incidence rate. And that you can express that in terms of percentage also. So in the case of placebo, recurrence rate is 8.8%, while in the case of apixaban treated people, recurrence rate is 1.7%. So just by looking at this incident rate itself, it's the story is pretty clear that the placebo group has the recurrence rate is far higher than apixaban group. So probably apixaban is reducing the recurrency of the thromboembolism. We can also calculate 95% confidence interval of these values. So it is nothing but a proportion. So that has been I have already taught you how to calculate in the binomial distribution. This is a binomial distribution, it's a proportion. So you can use modified Waltz method to calculate the 95%. So you can also write on one more column 95% CI. So it's very clear that the incident rate is far higher for the placebo group, that is 8.8%, comparing with the apixaban group, that is 1.7%. Now the term attributable risk or absolute risk, this term is very easy to comprehend. It is nothing but the rates that I have already explained to you, two incident rates, is just the subtraction of one from the another. So this is known as attributable risk. So it is the difference between two incident rates or proportions. We have 8.8% for the control or the placebo group, while 1.7% for apixaban treated group. The difference between these two values is nothing but 7.1%. We can also calculate the confidence interval of 95% confidence interval for this difference, the way I taught you earlier. So the CI is going to be 5% to 9.3%, that is the difference. So the drug lowered the absolute risk of thromboembolism by 7.1%, that is the summary, and with the CI you can also put that. So is it significant or not? All you have to do is what is the CI of this the difference? It is 5 to 9.3. Does it include our null hypothesis of 0 in it? No. So it is significant. So that is one easy way to conclude our study. Now how do you interpret the result in more formal manner? So if the entire interval, the interval refers to the confidence interval, 95% confidence interval. If the entire interval is positive, conclude that the probability that the outcome is present is higher in the population for the group 1, the first group, you see. The second group is called group 2. So if it is, everything is positive, that means there is no 0 in it. So if the entire interval is negative, that means the direction is opposite, you know. Conclude that the probability that the outcome is present is lower in the population for the group number 1. It is lower for the group number 1 if it is negative. Both confidence intervals are negative. While if it contains positive and negative, that means it contains 0. That means that do not conclude that the probability of the outcome differs for two groups. So it is not significant. That is what this confidence interval tells you about. Another term is called number needed to treat, that is called NNT, number needed to treat, you know. So this concept is also very clear. It is reciprocal of the attributable risk, is called number needed to treat, or NNT. So it is 1 divided by our attributable risk. So attributable risk that we calculated earlier is 0.074. So in this case 1 divided by this value is called 14. So it is 14. So it is NNT is 14. Now what does this number means? It means that for every 14 patients who receive apixaban treatment, you would expect to prevent the recurrent thromboembolism in 1 patient, while the other 13 would not get any benefit. You see, this is easy way for clinicians to interpret this risk in terms of how many of the patients will get benefit out of it. So you are giving this apixaban, you are prescribing the apixaban, then you can when you prescribe it, you know, you can actually see the pros and cons of it. If it is very inexpensive drug, this entity is rather too high. You know, you expect this drug to work only in 1 patient out of 14. You see, most of the patients, 13 will get no benefit. So if it is inexpensive, it's okay to prescribe, and if it doesn't have much side effect, you see. But if it is too expensive and it has got lots of side effects, probably you will think twice before prescribing this medicine for the patients. Another important term is called relative risk, also known as risk ratio. So relative risk is, instead of subtracting, you are taking the ratio of these two terms. So it is the ratio between the two incidence rate, or these are already in proportion, so it is ratio between these two proportions. So placebo divided by the drug is 8.8 divided by 1.7, that is 5.2. Now what does this 5.2, that is relative risk, means? Subjects treated with placebo were 5.2 times more likely to develop the recurrent thromboembolism than that treated with the apixaban. So this, you know, of course, there is two way. You can either take placebo first then to drug, or drug first to the placebo. This we first took placebo first to the drug doesn't convey much important information, but probably the drug on the numerator makes more sense. So let us take the other reciprocal. So reciprocal probably makes more sense than the other one, you know. So here the drug is on the top while placebo is on the bottom. So in this case it is 1.7 upon 8.8, that is equal to 0.19. So what does that mean? Subjects treated with apixaban had 19% risk of developing recurrent thromboembolism that of those treated with the placebo. So it's only 19%, so it's a lot of reduction, you see. So if you reduce this from 100 minus 19, you know, 19 is equal to 81. So you can also state the same thing as the drug reduced the relative risk by 81%. So that is a lot more easy to decipher, that kind of summary or statement. So it has reduced by to 81% reduction. Coming next is odds. Odds is the concept is very similar to the probability. We have seen that in the when we spoke about in the chi-square test, we saw about the Mendel's experiment. So he has a ratio in his mind. We can convert that into the probability. That is called the odds. So odds are the ratios, basically express the same thing what is being expressed as probability. So it is similar to the probability that an event will occur divided by the probability that the event will not occur. That is what the odds. So a probability of 0.5, that means odds of 1:1, 1 in 1. So odds of 1:3 is 1 case 3 control, for example, or 1 boy 3 girls. So this means a probability of 0.25. So see, that connection is very clear, 1 in 3. So 1:3 means total is 4. So out of 4, 1. So 1 divided by 4, that is 0.25. So that is how you are actually converting. So to convert the odds into the probability, 1:1, to convert that into the probability. So 1:1 is 1 divided by the sum, 1 plus 1. So 1 divided by 2, that is 0.5. So convert 107 to 100 ratio to the probability. How do you do that? 107 divided by 107 plus 100. So that is 207. So 107 upon 207 is 0.51. That is the probability. It's very easy. Reverse is also quite easy to convert probability into the odd. So 0.95 is a probability. So to convert that into the odd, 0.95 means 95. That is 95 is to 100 minus that value, 95. So 100 minus 95 is 5. So 95 is to 5. So that you can simplify to divide by 5. So each value will be divided by 5. So you are going to get 19:1. Another example is 0.57. How do you convert that? 57 is to 100 minus 57 is equal to 43. So 57 is to 43 is the odds of it. So now coming to the odds ratio. Odds ratio is of an event is a probability that it occurs divided by the probability that it doesn't occur. Odds ratio is the event of the group 1 divided by the odds of the group number 2. So it is basically sample odds of the outcome of each group. That is how you are actually calculating the odds ratio. So odds ratio you can estimate by odds ratio, your N1 divided by N2 or N3 divided by N2. So that way you can actually, this is basically two ratios. Two are actually the proportions. You're dividing one ratio divided by second ratio is called odds ratio. Odds of one event divided by odds of second event is the ratio between these two odds is the odds ratio. And this odds ratio also you can also do that. You can also calculate the 95% CI of the odds ratio by plugging into this equation, which is actually not practical easily for pen and paper, but it's much easier to calculate this odds ratio confidence interval using a computer, and also there are several online calculators are available. So odds ratio is choice to summarize a case control study. So it is a retrospective study. The case control study is not prospective, it is a retrospective study, and usually in case control study the controls are far higher than the cases. So why not, you might think, attributable risk or the absolute risk or even risk ratio, why not? So it doesn't make any sense for the case control study because the controls are deliberately chosen, and we are sure that usually it's far higher than the cases. So one example is given in this table, that is NSAID user, and what is actually the risk of this one particular disease for this NSAID user and NSAID no user. NSAID means non-steroidal anti-inflammatory drugs. So if you do this way and if you calculate the attributable risk, so it is basically coming to be 0.18. So can you say that 18% of NSAID users will develop GBM disease? That is incorrect, because this control, I can actually increase the control or decrease the control upon my own discretion, right? Had I decreased the control, then this percentage will be less, because it depends upon the total. So case control study is a retrospective study. I've already explained what this case control study in the first module. It's the second module itself. Cases are 137 self-reporting patients with glioblastoma milliforme, that is GBM, the disease, while controls are 401 in the population based on the individuals matched the cases with report to the demographic factors. So this is our data set. So you can actually calculate this one, the odds and odds ratio. So for odds ratio, it's actually very easy to calculate by cross multiplying and dividing. So cross multiply one odd to another odd, the numbers you simply cross multiply, divided by the other cross, multiply the other two numbers. So that is called the odds ratio. It's actually very simple to calculate. And there is also a formula for to calculate 95% confidence interval of the odds ratio. You can plug into these values to calculate exact 95% CI, or you can calculate this by the software methods. So you can easily see that. How do you interpret this odds ratio 95% CI? So if the entire interval is above 1, conclude that the probability of the outcome is present higher in the population for the group 1. So remember, the null hypothesis is 1, because this is basically, it's a ratio. So the ratio means both numerator and denominator are equal. That means you are going to get 1. So that is why, is it 1 or above 1 or below 1? That is the question here. If the entire interval is below 1, conclude that the probability that the outcome is present is lower for the group 1. So if it is above 1, that means that it is higher for the group 1, while if it's lower than 1, that means that it is lower in group 1, higher in group 2. So if this interval contains 1, that is our null hypothesis. That means that p-value must be higher than 0.05, and it is not significant, isn't it? Do not conclude that the probability of the outcome differs for two groups. So that is how to interpret the different odds ratio. There are several tests of statistical significance for the categorical data, including for correlation. You can use chi-square test of independence that we have discussed already in module number 18. You can also perform Fisher's exact test that we are going to explain in this module. For model fitting or regression, you can do chi-square test of goodness of fit, that I explained that in M18. And also you can use binomial test. So we are going to explain in this module. What is Fisher's exact test? So as the name says, it provides the exact p-value. It's not like a it's an absolute p-value. It is not a approximation, or it's not an approximate p-value like in the case of chi-square test. For 2×2 contingency table or two-way table that is frequently used in case control study, the best test is called Fisher's exact test. It can be found at this link that you can click on it. It is there in the web link section. Do check it out. It's very easy, and it calculates the exact p-value, as I told you, but this exactness of the p-value is also highly criticized by many statisticians. It is exact p-value, but that is not really makes much sense in scientific thought. So there are two hypotheses for this Fisher's exact test. The first hypothesis, or the null hypothesis, is that the variables are statistically independent. The two variables are not dependent. And while the alternative hypothesis is that the variables are statistically dependent. So this is what it is. So it is the test of the correlation of these two variables. Performing Fisher's exact test is pretty easy. All you have to do is to put on the values into these 4 cells. Because it's a two-way table, just have to put these values into the 4 cells, and you can mark the headers as well, what is placebo and what is apixaban, the columns as well as the rows. You can put the labels in it. And what is going on in this test is actually very simple, and it is very intuitive formula. As you can see it here, the formula is pretty simple and intuitive. It's all about factorials. A you just have to mark these 4 quadrants as A, and one is B, another is C, another is D. It doesn't matter which is A, which is B, in any order, whichever order is fine to you, you can just mark it. Then just have to plug into this formula. A plus B factorial multiplied by C plus D factorial multiplied by A plus C factorial multiplied by B plus D factorial. So all combinations of factorial, you multiply it, divided by A factorial multiplied by B factorial multiplied by C factorial multiplied by D factorial multiplied by N factorial. N is the total number of the factorial. So it's seemingly simple, but if you have a huge number, then even using a computer, this formula, it's very difficult. So it is very interesting, but look, it is highly intuitive, but it's not practical if you have a huge number. So you can see that this is what the Fisher's test summary table here, and what is the p-value of this test. Everything you can make inferences out of it by performing the online test. So how do you interpret this p-value? If the null hypothesis is true, there is less than 0.01% chance of randomly picking the subjects which are as large or larger than the difference in the incidence rate. So here this chance is pretty low, 0.01%. So then you conclude that it is statistically significant. So this is another example, the gun sale versus homicidal rate. You can just put this one into the Fisher's exact test and calculate the p-value, and all these things you can perform it and see that. Another important test is called binomial test, especially useful for the proportions. When there are only 2 categories like head and tail in the coin flipping, or male or female in the gender, the best option is to go for the goodness of fit test is called binomial test, which calculates the exact probabilities using the binomial equation. No, it's not like chi-square probability, which is approximate. This is exact, like Fisher's exact test. So the formula is also pretty simple. The binomial equation, there is P of x is equal to NCX, or sometimes you can call it as NCR, that is nothing but combination equation, multiplied by P power x multiplied by Q power n minus x. That is the formula here. What is P? P is probability of success in one trial, while Q is 1 minus P, or probability of failure in one trial, that is the Q. And n is the total number of trials, while x is the total number of success in n trials. So that is the binomial equation, and we will also see about this binomial probabilistic distribution in one of the next modules. So binomial test is also available. Online version is available at this link. I'll be putting up in the web references. I suggest you to go check it out and do some works yourself, and to interpret the p-values. So p-values inferred from the chi-square tests are only approximations but not exact, but in the case of binomial test, these are exact. The only issue is that binomial test can use only in certain situations, not all situations where the p-values are preferable. So the hypothesis for the binomial test is very simple, straightforward. That is, the null hypothesis, the frequencies are same. So, or you can say that the model fits the data well, while in the case of alternative hypothesis is that frequencies are not same. That means that model do not fit the data well. So if you perform the binomial test, not sign test is something else. So binomial test, if you perform, then you will see that exact p-value, so which is almost identical to the chi-square p-value that we found, that is 0.031. So you can see that, you can interpret that way. One example is that amongst the total number of students in CUPB, 61% are females. So our difference between the number of females and males statistically significant at 95% CI. You can perform this one as an assignment, and we can discuss this matter in the discussion section of the course. So in summary, attributable risk is the difference between the two incident rates or proportions. So that is called attributable risk. It is difference only, or it's also known as absolute risk. Reciprocal of the attributable risk is known as number needed to treat, or NNT. Relative risk, also known as risk ratio or RR, is a ratio between the two incident rates or proportions. Inverting the numerator and denominator will go in the different perspective. of the RR. So concept of odds is similar to the probability that an event will occur divided by the probability that the event will not occur. That is what is odds is all about. Odds ratio is a choice to summarize a case control study or which is a retrospective study, the odds ratio. And remember that the odds ratio is very similar to the attributable risk. The relative risk, actually not attributable but relative risk, if the disease incidence is very low. So rare diseases, then this is perfectly fine. If it's less than 10% in the population, odds ratio can be used as an approximation or a proxy for inferring what is this relative risk. But these two terms are actually quite different, perspectives are different, but still you can use it as an approximation. For 2x2 contingency table, which is frequently used for the case control studies, the best test is called Fisher's exact test. So the test that means the test for statistical significance for p-value calculation. So when there are only two categories like head and tail in coin flipping or male and female in the gender, the best option is to go for a goodness of fit test. For the goodness of fit test is called binomial test. Rather than going for a chi-square, it's better to go with the binomial test if you if you have only two categories. So to calculate the exact probabilities using binomial equation. Thank you so much for listening, and I hope you will enjoy.